Hi, how's it going? In the last video, we covered till host semantics in the interchain standards. We covered till host client. Today, we'll be covering client semantics. This standard specifies the properties that consensus algorithm of machines implementing the IBC protocol are required to satisfy. These properties are necessary for efficient and safe verification in the higher level protocol abstractions. The algorithm utilized in IBC to verify the consensus transcript and state subcomponents of another machine is referred to as a validity predicate. We'll talk a little bit more about this later in the presentation. And pairing it with a state that the verifier assumes to be correct forms a light client, often shortened to a client. However, in this video, I'll be referring to it as a light client only. This standard also specifies how light lines will be stored, registered, and updated in the canonical IBC handler. The stored light client instances will be introspectable by a third-party actor, such as a user inspecting a state of the chain and deciding whether or not to send an IBC packet. Uh, in the technical specifications of client semantics, there are a few things that need to be defined, which are already defined in ICS 24. If we don't mind, we can go over there in the host requirements, go to definitions right here, and have a look at um, whatever is needed, an identifier, path, and stuff like that. Um, yeah. Commitment root is defined in ICS 23. It must provide an inexpensive way for downstream logic to verify whether key value pairs are present in state at a particular height or not. Consensus state is an opaque type representing value of the validity predicate. Consensus state must also be able to verify state updates agreed upon by the associated consensus algorithms. Client state is an opaque type representing the state of a client. A client state must expose query functions to verify memberships or non-membership of key value pair and state at particular heights to retrieve the current consensus state. More semantics and data structures are covered better in the ICS manual available on the Cosmos repository. For that, all we need to do is go over here, go to the second ICS number, and you can go a little bit down. Stuff are better defined here. You can go a little down and check specifically what we need. You've got your data structures right here. Now let's talk about connection semantics. I'm sorry. This standard document describes the abstraction of an IBC connection, two stateful objects on two separate chains, each associated with a light client of the other chain, which together facilitate a cross-chain sub-state verification and packet association. All of this comes together for IBC. You have to keep that in mind. A protocol for safely establishing a connection between two chains is described. Implementing blockchain should be able to safely allow untrusted actors to open and update connections. Um, I'll skip this for now. There's a lot of things that we need to cover in the technical specifications of connection semantics. Instead, I'll go over to the report. Let's go back here. Let's talk about port allocation for a minute here. This standard specifies the port allocation system by which modules can bind to uniquely named ports allocated by the IBC handler. Ports can be used to then open channels and can be transferred late or later released by a module which is originally bound to them. A port is a particular kind of identifier which is used to permission channel openings and usage to modules. Once a module has been bound to a port, no other module can use that port until that module releases it. A module can, on its option, release a port or transfer it to another module. A single module can bind to multiple ports at once. Ports are allocated on a FCFS basis, which is first come first serve, and reserved ports for known modules can be bound when the chain is first started. Let's talk about channel and packet semantics. The channel abstraction provides messages delivery semantics to the IBC protocol in three categories: ordering, exactly once delivery, and module permissioning. A channel serves as a conduit for packets passing between a module on one chain and a module on another, ensuring that packets are executed only once, delivered in the order in which they were sent, if necessary, and delivered only to the corresponding module owning the other end of the channel on the destination chain. We will see this more in action a bit later. Desired properties would be efficiency exactly once delivery. We don't want a situation where one packet is delivered twice, even if as a failsafe. We've got ordering and permissioning. Ordering is not mandatory unless and until the sender requires it to be. This is a data flow visualization. You can pause the video here and have a look at it. Alright, let's move on. In case you don't really get anything in this, just refer to the documentation. It's described pretty well in detail there. Yeah,